Okay, thanks to the organizers for inviting me. It's a pleasure being here. It's a long day for all of us. I'm as tired as anybody else. So I kicked out a few slides and tried to go as quickly as possible. So I changed the title. It's not about anti-arrhythmia therapies. I will reduce it to defibrillation only, which was the main point anyways. So at first I try to make a point, why should we complement experiments with in-silico models. There are a few things you can do with computer models which are not that easy to do with experimental methods. So with computer models you can quantitatively evaluate known relationships to provide a mechanistic link between experimental observations. The other thing is you can observe all quantities of interest at almost, theoretically, at almost any desired spatiotemporal resolution over the entire domain of interest. So you can look into the heart. You can see the 3D volume. This is very hard with experiments, as Olivier mentioned in his talk. You can do a parameter variation without undesired side effects. This is straightforward in a computer model. It's very hard to do in an experiment. So change one parameter without changing another one. So the downside is the model parameterization may be very challenging because there are tons of parameters in the models. We don't know any of them with a better accuracy of 10%, and there's a huge variability between individuals and between species. The other downside of models is there are unknown mechanisms are not accounted for. So experimentalists tend to shorten this discussion simply by saying it's not the real thing. So and it's actually, we don't know. And any mechanism that is unknown cannot be accounted for in the computer model. So, but I think there's a mutual dependency, or dependency maybe is the wrong word. So modeling definitely requires experiments to build the model upon the data we get. But on the other hand, experimental work can benefit a lot from modeling by bridging gaps where no experimental data are available. So the ping pong between experiment and computer model, I'll like to talk a little bit about that in the context of defibrillation. So defibrillation is basically a solved problem. It's a very successful therapy. The problem with it is it's extremely painful, and this traumatizes patients, and it reduces the quality of life. So in this sense, it's not a solved problem. To improve the therapy, a better understanding of the underlying mechanisms is required, and one of the things we're interested in is to understand how the shock interacts with deeper layers in the tissue, with the polarization in the mid-myocardium. So experimentally, as we've heard, this is very hard to do. So the group of Vladimir Fast, they came up with a new method. They proposed a method with which you can measure mid-myocardial polarizations with optical mapping. So the idea is like that. So you take a wedge, you press the transmural face of the wedge against a glass plate, and you optically map through that to observe observations in the depths of the myocardium. So this certainly raises the question, so is this really the same thing as what we would have observed in the intact heart? With the computer model, this is fairly simple to check. So we can build a simplified wedge model. We can quickly change the boundary conditions here against the glass plate. We can manipulate the fiber rotation in the tissue. And we've done some computer simulations, and clearly what you can see here, so this would be the intramural plane with 3 different fiber configurations. Here's the most general case with fiber rotation. So this would be an intramural plane, and this here would be the optical mapping plane. And these are the shock-induced changes in delta Vm along this line. As you can see, the potentials match perfectly. So experimentalists can do that, which is good for the experimentalists. So the theoretical conjuration, so at the first glance it's a little surprising. You rip it out of the heart, press it against the glass plate, and you map it, and it's the same thing as an intact heart. But if you look at what's going on from a theoretical point of view, it's not that surprising. So here, for instance, that's the fiber orientation in the intact heart. So if you press it, the wedge against the glass, which is an isolator, it's basically a symmetry plane. So you're introducing here a discontinuity that is not present in the intact heart. So why does this not cause an artifact? So the reason for that is if you look at the generalized activating function, it's just a rewritten version of the Biedermann equation. So here is the term that's the activating function, and you can see that's the extracellular. That's the term that describes the interaction of the extracellular field and how it drives the change in the transmembrane voltage. So you can split this function into an S1 and S2 component. As you can see here, the S2 component here is 0 because we have 2 plate electrodes in a homogeneous field, so there is no, this term does not contribute. And this term here, that would generate an artifactual component because here the heterogeneity of the tissue here is artificial. So the reason why this doesn't show up in the results is because this is weighted with a 0 field. So the heterogeneity, the artificial heterogeneity of the tissue is in this direction, but the field goes in this direction. There's no field component to give it the weight, so it does not change any artificial polarizations. So wedge preps, they work for a very specific setup only a homogeneous field with impermeable boundary conditions, and they cannot be used for predictions of intramodal polarizations patterns for an ICD configuration, for instance, because then we will have artificial terms that are not present in the intact heart. So under these conditions, wedge preparations can work, but there's another experimental observation. For instance, so the method relies on enforcing impermeable boundary conditions. But then the experimentalists reported, well, no matter whether you enforce it or not, we get the same results. So if we do the same thing in a computer model, here, so we stimulate, bring the entire wedge up to plateau, and then we apply a shock, 26 volt per centimeter in this case. You can see there's a huge difference between the 2 boundary conditions. So you can see that here. So with permeable boundary conditions, you get a completely different shock-induced polarization across the wall here. So the patterns are completely different. So there's a huge discrepancy between experiment and model. So, and if the experimental results were correct, the bidomain equations would be wrong. So this is something we cannot reconcile easily. There's another interesting observation with this particular setup. So if they increase the shock strengths, all of a sudden they only see negative shock-induced polarizations across the wall, which is basically a little surprising because it basically says current is leaving the intracellular space all over the entire observation area. So which offends somehow the law of charge conservation. So we thought one possible explanation was, okay, the heart is discontinuous and you get polarizations of opposite polarity across the discontinuities. And due to the asymmetry of the membrane, the negative polarization overtakes the positive polarization, and at the end you end up just seeing, due to the averaging, you just can see the negative polarizations. So we tried to model that in a computer model. We simulated optical maps as well, and what we could see is optical mapping, it introduces somehow a little bit of bias towards negative polarizations, but even with a strong shock, we always had a little bit of positive shock-induced polarizations as well. And by the way, this would be in the wrong boundary conditions. So this is with permeable boundary conditions. So with impermeable boundary conditions, we could not get any match with optical maps. So computer models won't be able to predict this because it's a disagreement with the underlying equation. So the bidomain equations enforce charge conservation, and this cannot lead to this polarization pattern. So computer models can also be used to scrutinize experimental data. So, but the modeling I've shown is probably not very well suited for developing anti-arrhythmia therapy. So recently what I'm more interested in is in-silico modeling. So based on, you have a set of imaging data. There's no single imaging modality that is ideal for generating models. So you have a bunch of data, different modalities. So the data, by the way, are from Peter Cole's lab. So the idea is you fuse that data into one consistent image stack, and so that everything overlaps in the same space, and then you use the parameters of that space to generate the anatomy of your heart and also to parameterize your model. So this is not shown here, but actually for computer simulations there's a complicated ping pong between the actual simulations and going back and forth between the tags, so or the information you get from the image stack, because you start with ballpark figures and out of the box you never get the right activation sequence. So if you have experimental data, you have to tune. This is actually a complicated inverse problem to figure out the right parameters for parameterizing your model. So this is something I got interested in. This is a standard. So we generated this anatomically highly realistic model of a rapid, and I started to use that for simulating defibrillation shocks delivered through an ICD setup. So here would be an ICD electrode. So that would be the heart. The question is, with the standard configuration, I'm interested in predicting the gradient, the potential, and what does it do to the transmembrane voltage. In particular, I'm interested in the components of the activating function, but I haven't computed that yet. So the thing is, so we deliver a shock through that electrode here, and then we look what's going to happen in the heart. So this is a passive heart only. It's not an ionic model. So if you look, so the interesting bit here is the gradient. So we have tested different shock strengths here. So the shock strengths are not really, these are the gradients right at the electrode. They're really high. So this is not the shock strengths that any part of the tissue would actually experience. But that's what we measured at the surface of the electrode. So here we scaled the gradient just to show it up to 4 volts per centimeter. So as you can see, even with a fairly strong shock, the voltage gradient, the 4 volts per centimeter line, is very close to the electrode. So what this means is, as I said before, the shock effect depends on gradient and structure. So either we need a minimum gradient heterogeneity required to evoke an active response in homogeneous tissue, that would be the S2 term, or we need a minimum gradient required to evoke active responses in heterogeneous tissue, that would be the S1 component. For instance, any effort like unpinning relies on the S1 component, so you need a minimum gradient over the entire domain to evoke an active response at the tissue heterogeneity. If you don't have that, you don't get an active response. So what I'm saying here is, with a standard ICD setup, this is very difficult to achieve because the gradient, as is known, it drops off with 1 over r squared. So it's very hard to have a high gradient over the entire heart. In an experimental setup with plate electrodes, this is simple to achieve, but not with an ICD setup. So you are in the dilemma. You have a very high gradient near field, but a low gradient far field. Am I running out of time? Oh, okay, then I go quicker. So one interesting candidate for modeling is the Purkinje system. So Mark Boet has shown something. I'm just gonna show one simulation to show which the Purkinje system may play quite an important role in the formation of re-entry. Here's a bundle re-entry. The simulation was conducted by Ed Wigmont. So that's something I'm interested in, and also in improving the models of the Purkinje system, which is topologically very complex. It's actually quite a challenging modeling problem. And the other thing is, I want to show this one simulation here. So with these highly complex models, we're interested in sweeping the parameter spaces. We're interested in changing electrode configurations, changing short protocols, changing the membrane and all that. This here is a simulation with the most recent Marchand-Shifarov model of the USLA group. So the question is, with in-silico models, they are only valuable if we can compute things fast enough. So this does not work. Okay, then. Oh. Okay, here we go. So, so if it takes forever to compute that, the model is useless. So, but on modern high-performance computers, it's fairly easy to compute a sequence like that. For instance, in monodomain mode, it's about 4,000 times slower than real time. Bidomain, it would be 65,000 times slower than real time. Actually, with a more aggressive setup, we can be much faster. So as a ballpark figure, you can say it's 1,000 times slower than real time. The same would apply for a human heart, because a human heart would scale up to much higher processor counts. So here's some data I got from Stephen Niederer, who is running human simulations, and it was 23,000 times slower than real time, and it came probably in a bigger computer done with the factor 1,000 as well. In the future, with the petaflops high-performance computing hardware, we'll see a speed up of 2 to 3 orders of magnitude. And in 2 to 3 years, we will get today's high-performance computing performance on desktop computers with accelerators probably. So that's my prediction, and I'm pretty sure we can achieve that. So here's the summary. So ping pong between experiment and computer modeling may provide additional insights that cannot be gained otherwise. So virtual experiments with anatomical and functionally highly detailed computer models of the entire organ are feasible today. Blah blah. So the next generation HPC hardware may revolutionize tissue and organ level modeling by boosting performance over the next few years to enable near real-time solutions. However, so this performance gain will not come for free. So a huge, a major software revamp is required to squeeze out the performance of the next generation computers, because they will be quite different from what we are used to. So thanks for your attention. Happy to take any questions.
So one of the concerns about the wedge preparation and defibrillation is if you look at the extracellular potassium accumulation occurs as a function of time of fibrillation. And then it reaches, and as potassium accumulation rises, you can see the frequency of the fibrillation changes and slows down, and finally you have total arrest. So this time course is going to be very different in a wedge preparation, where it may not occur because you've cut the vessels, and the potassium in the T-tubules is going to take on a very different pattern. And that would be my concern about comparing a wedge to an intact heart. And so maybe both have, the model has to be wary of that issue.
Yeah, I don't think it's a very good experimental model for studying transmodal polarizations to start with. This is an additional concern. And the other concerns I did not mention is when you cut that, you have the healing overlayer. We don't know the exact electrophysiological status in that. And when you optically map that,
there are ionic leaks that occur on the fingers.
Yeah.
Peter, is it quick?
Yes, it's quick, Gernot. Beautiful talk. One question. That scaling, or that factor of 1,000, how much larger would it be if I wanted to add mechanical activity?
I'm not the mechanics expert. Probably Nick could comment on that. But usually, I'd say mechanics is somehow faster to compute.
15%.
So a factor of 2.
So not an order of magnitude.
No.
Okay, we should probably wrap up there. Thanks everybody for talking this afternoon. We're going upstairs for the wine reception, so you can go upstairs a little way. There'll be some wine and beer and soft drinks as well. We thank